Swayam Prabha. Digital India. Educated India.
A warm welcome to the 16th lecture on the subject of digital signal processing and its applications. We will take a minute to recapitulate what we did in the previous lecture. We had been looking at the rational Z transform in the previous lecture, and we had evolved different ways to deal with the inversion of the rational Z transform. Essentially, we had looked at partial fraction expansion and the use of the derivative, the derivative of the Z transform. So, we multiply the sequence by n when you take the derivative. Essentially, there is an association between multiplication of the sequence by the time index and taking a derivative in the Z domain. Of course, you do need to multiply by the factor minus Z after taking the derivative and so on, but there is a relationship between multiplying by n or the time index or a polynomial in the time index. So, polynomial in the time, so let us write this down. You see, polynomial in the time index, polynomial in time index n. So, essentially something of the form summation k going from 0 to say m a k n raised to the power k multiplied by x n involves taking essentially a linear combination of the kth derivative. So, this corresponds to summation k going from 0 to m. Now, please note, we should interpret this carefully. What I am saying here, minus z d dz to the power k x z. This means applying the operator, first take the derivative with respect to z and then multiply by minus z. Together this should be treated as an operator. And for example, if you are doing this twice, if k is equal to 2, what you mean is take the derivative with respect to z, multiply by minus z, then take the derivative again with respect to z and multiply by minus z. So, apply the whole operator minus z d dz twice. That is how one should interpret it, right. So, this multiplied by bk, okay, some bk, some constant. So, essentially there is a one-to-one association in the z domain between a polynomial in the time index multiplying the sequence and a polynomial in this operator minus z d dz multiplying the z transform or operating on the z transform, all right. So, I have also asked you to put down this relationship precisely by using inductive reasoning, right. I have left it to you as an exercise to do that. And based on this principle, we could see that we could handle any z transform here, any rational z transform, right, based on this principle and partial fraction expansion. We can handle any rational z transform. Now, one observation that we made last time was that the rational Z transform is kind of frequent in occurrence. That is why we said that we were spending so much of time on the rational Z transform. We shall take the next few minutes to understand why this is the case. Why is it that the rational Z transform is so important? Why does it mean a lot to us? In fact, let us assume that we have a system described by a system function which is rational. So, for example, let us take a concrete system as an example where the transfer function or the system function is rational. Consider an LSI system with system function let us say 1 minus 1/4 Z inverse divided by 1 minus 1/3 Z inverse into 1 minus half Z inverse. This is capital H of Z. It is essentially the Z transform of the impulse response of that system. Now, let us expand, let us draw out Hz. So, Hz can be rewritten as 1 minus 1/4 Z inverse divided by 1 minus 1/3 plus half Z inverse plus 1/6 Z raised to the power minus 2, which of course becomes 1 minus 1/4 Z inverse, 1 minus 3 plus 2 makes it 5 by 6 Z inverse plus 1 by 6 Z raised to the power minus 2. Now, what is Hz? Hz is the ratio of the output Z transform to the input Z transform. In fact, that is obvious because the input Z transform multiplied by Hz would give you the output Z transform. Xz multiplied by Hz would give you Yz. And therefore, another way to understand the system function is the ratio of the output Z transform to the input Z transform. This also tells us something about LSI systems. If you look at the ratio of the output Z transform to the input Z transform, and if you find that this ratio is independent of the input, then the system is LSI. That is another way of looking at it. So, in the Z domain, the fact that the output Z transform divided by the input Z transform is independent of the input makes the system LSI. All right. So, in effect what we are saying is that Hz, which is Yz by Xz in this case, is 1 minus 1/4 Z inverse by 1 minus 5 by 6 Z inverse plus 1 by 6 Z raised to the power minus 2, and we can of course cross multiply. We can cross multiply to get Yz into 1 minus 5 by 6 Z inverse plus 1 by 6 Z raised to the power minus 2 is Xz into 1 minus 1/4 Z inverse. And we can go back to time, go back to the natural domain by taking the inverse Z transform on both sides. So, of course, it is very easy to see that you would get Yn here, and here you would get minus 5 by 6. The inverse Z transform of Z inverse Yz is y of n minus 1, essentially y delayed by 1, and so on. So, one can take the inverse Z transform on both sides. We will denote this as the inverse Z transform. You have Yn minus 5 by 6 y of n minus 1 plus 1 by 6 y of n minus 2 is xn minus 1 by 4 x n minus 1. And of course, we can rewrite this. So, you have what we want to do ultimately is to write Yn in terms of past values of y and x and its past values. So, we can keep Yn on one side and move all the other terms to the other side. So, we have y n is 5 by 6 y n minus 1 minus 1 by 6 y n minus 2 plus x n minus 1 by 4 x n minus 1. And this is an example of what is called a linear constant coefficient difference equation. It is abbreviated by LCCDE. Difference equation. Let us understand the terms one by one. Difference equation is a relation between the input and the output in the sampled natural domain. The difference equation is a relation between the discrete input and the discrete output. A constant coefficient difference equation is a relationship where the constants that are involved, where the multipliers that are involved are all constant. So, here these are the multipliers 1 minus 1/4, 5 by 6 and minus 1 by 6, all of them are constant. That is why it is a constant coefficient difference equation, and linear. It is linear because it obeys, this entire input output relationship obeys the principle of superposition. That means it obeys additivity and homogeneity, and therefore, this is called a linear constant coefficient difference equation. If you drop the terms one by one, for example, you could have a constant coefficient difference equation which is not linear. For example, suppose in this equation you brought in y of n minus 2 the whole squared, then it would become a constant coefficient difference equation, but not linear, and so on, right. And there could be, of course, a linear equation, but not constant coefficient. For example, some of these terms could depend on n here, right. So, each of these terms in the expression LCCDE is important. Now, LCCDEs are very important. You see, this kind of an equation is very fundamental to realizability. In fact, let us spend a minute on seeing how you can realize this very relationship here. That is, how would you translate this into a hardware structure or a software structure? We can see this right away. So, in fact, suppose you happen to have, a circuit which constantly generates yn. That means you have, let us assume that you have a timing mechanism which times the samples, the sampling points and the samples. In every unit time, one sample of the input is fed and one sample of the output is generated. So, you have a timing mechanism. You have to have a timing mechanism anyway. Now, in that timing mechanism, what you do is introduce what you call memory. So, you introduce a delay buffer, which we will denote by D. In fact, introduce two of them. So, when you feed yn to a delay buffer, what you get is y of n minus 1. That means a delay buffer stores the previous value of the output, stores the previous value of the input given to it. So, in this case it is yn, but in general a delay buffer stores the previous value of the input given to it. And of course, here you would get y of n minus 2. And similarly, you could have a delay buffer operating on the input, and that would give us x of n minus 1. Now, what does this equation tell me? This equation tells me that I have taken y of n minus 1, multiplied it by 5 by 6. I have taken y of n minus 2 and multiplied it by minus 1 by 6. I have added these two. I will show addition by a summation here. I have added these two. I have also taken the input and added to it minus 1 by 4 times the input delayed by one sample. And I have added these two together and thus generated the output. I have taken care here to allow only for what are called two input adders. So, we will assume that all the elements need to be of uniform structure. So, all the adds are of two inputs. Of course, you could have additions with more than two inputs, because addition is a commutative and associative operation. You can add more than two at a time, but we will assume for the sake of modularity and implementability that you use a two input adder. So, what we have done is to realize this relationship, this linear constant coefficient difference equation, by using three kinds of elements: delay buffers, these D's, multipliers, constant multipliers, and two input adders. Let us write that down. We can realize means translate into hardware or software. A linear constant coefficient difference equation, and hence a rational system function. A rational system function is realizable. It is realizable because you can use a finite amount of hardware and software to translate it into an implementable structure. Finite is important. What kind of hardware and software have we used here? Let us again list that down. Elements that are used: one sample delay buffer, which we denoted by D, constant multipliers or scaling units, two input adders, these are three kinds of elements that we used. Of course, you can very easily see that each of these elements can either be thought of as a hardware element or as a software element. For example, if you think about the one sample delay, you could think of it as a little program statement which stores the previous value and keeps it at a memory location. And of course, in hardware you can think of it as a register or a combination of registers. Similarly, a constant multiplier can be thought of either as a hardware element or as a software element. In software, it is a one line multiplication by a constant. In hardware, essentially a multiplier implemented with any of the known multiplier algorithms, constant multiplier of course. And you know that there are very efficient ways of implementing multipliers, if you know them to be constant multipliers. For example, one could use distributed arithmetic or any other efficient way of doing multiplication, Booth's algorithm if you like, right. Anyway, so much so for the fact that, and two input adders, again we know how to do that with 2's complement or any other structure, right. So, we know how to implement it in hardware, and of course, in software again it is a one line statement. So, all of these are really unit statements in software or unit elements in hardware, modular elements in hardware, and with a combination of them we can realize a rational system function. So, rational system function is realizable. Now, to contrast, let us take an example of an irrational. You see, all this while we have been saying rational. So, the natural question that comes to mind is, can you have an irrational system function? So, can a system function or can a Z transform be irrational? And the answer, of course, has to be yes, of course. Take x z is e raised to the power z inverse with the region of convergence mod z greater than 0. Now, note that here you cannot include the point z equal to 0 in the region of convergence. In fact, this is an example of what is called an essential singularity. You know, in some sense, a singularity of infinite degree, we will see in a minute. Now, e raised to the power z inverse is very easy to expand. You know, those of us, all of us would have been exposed to the Taylor series at some right. So, the Taylor series expansion of e raised to the power z inverse essentially summation n going from 0 to infinity z inverse raised to the power of n divided by n factorial, with 0 factorial defined as 1 and n factorial defined as n into n minus 1 factorial. This is well known. This is essentially the Taylor series expansion of e raised to the power of x. Now, when we write down this Taylor series expansion, it is very easy to identify what sequence corresponds to this x z. That is very easy to do. In fact, it turns out that this sequence x n would simply be 1 by n factorial u n, where n factorial has been defined already. And u n you know, u n is the unit step. In fact, very interestingly, if an LSI system were to have this impulse response, suppose x n were the impulse response of an LSI system, we could ask whether the system is causal and stable. And it is very easy to see the system is of course causal, because the impulse response is 0 for n less than 0. So, of course, if this were to be the impulse response for an LSI system, the LSI system would be causal. Would it be stable? How would we answer the question? We would need to look at the absolute sum of the impulse response. And in fact, the absolute sum of x n is very easy to calculate. So, summation n over all integers mod x n is very easy to calculate. It is essentially summation n going from 0 to infinity mod 1 by n factorial, which is essentially 1 by n factorial, because n factorial is positive. And this is very easy to evaluate. This is essentially e raised to the power of x evaluated at x equal to 1. This is e, the standard Neperian base, and that is of course finite, and therefore, this is absolutely summable, and therefore, the system is stable. So, if a system were to have this impulse response, it would be both causal and stable. However, e raised to the power z inverse can never be written as a ratio of two finite series in Z. It is impossible impossible to write e raised to the power z inverse as a ratio of two finite series in z. Z or z inverse, does not matter. And therefore, x z is irrational. And concomitant with that is also that if this happened to be the system function of some LSI system, which it can be, nothing stops it from being the system function of an LSI system. If it were, that system is not realizable. That means there is no finite hardware, or at least no known, at least today, there is no known finite hardware or software structure which can realize this system. As of date, irrational systems are unrealizable in hardware or software. So, irrational systems are not, see, we must not confuse irrational with unstable or non-causal or something of the kind. Rationality or irrationality for an LSI system is a property over and above the other properties, causality, stability. Yes. Of course, rationality has a meaning only for LSI systems. One cannot talk about rationality or irrationality when the system is not LSI. In fact, not only LSI, it must be LSI and its impulse response must have a Z transform. Otherwise, there is no sense in talking about rationality or irrationality. So, now we have a classification of LSI systems. You have the whole class of LSI systems. They are characterized by the impulse response. Among them, you have a smaller class whose impulse response has a Z transform. That means that the Z transform converges somewhere in the Z plane. And among them, you have Z transforms or LSI systems which have a Z transform, and the Z transform is rational. That is the innermost core, which we are calling rational systems. And those are the systems that we are going to design, implement and build. Now, we share a very important problem or challenge. You may look at it in either sense, which nature poses, whether it is in discrete time or continuous time. The ideal systems that we want to realize are irrational. We shall see that very soon. The ideal system, when we put down ideal specifications for what we want to do, the corresponding system turns out to be irrational. And the whole game that we are going to play for several lectures all over the subject of filter design is to approximate this irrational ideal by rational systems. The rational systems, see, nature in engineering, this is probably a frequent occurrence. What we want is what we cannot realize. What we can realize is often not what we want, but we have to draw a compromise between the two. That is often the case in engineering and technology, and discrete time processing is no exception. Anyway, let us look a little more at rational systems and specifically linear constant coefficient difference equations. Now, you see, we have a linear constant coefficient difference equation. Let us take, for example, the linear constant coefficient difference equation that we had a minute ago. Y n is 5 by 6 y n minus 1 minus 1 by 6 y n minus 2 plus x n minus 1 by 4 x n minus 1. Now, I want to make a few remarks about solving such difference equations. By what I mean by solving is you are provided with the value of x n over a certain interval of time. So, let us take an example. Let us assume that x n is known. known for n equal to, let us say, capital N1 to n equal to capital N2. In particular, capital N1 might be 0 and capital N2 might be, say, 20 or 100, right. So, what we are saying is, in a sense, is that you know the input over a certain interval of the natural domain. Okay. So, the input is known over an interval of the natural domain. The output is known for some pre-specified points. Example, suppose N1 is equal to 0, N2 is equal to 20. We continue this. We are given y of minus 1 and y of minus 2. So, you know the what we call the initial values, and we wish to obtain y of n for n equal to N1 to N2, namely 0 to 20. How would we proceed in this case? Well, the approach to proceeding is to, for a moment, assume that this difference equation lasted forever. So, the approach is assume the difference equation lasted forever, assume the LCCD held forever. Find the corresponding system function. What do you mean by the corresponding system function? The ratio of yz to xz. And what is that corresponding system function here? You know it. It is 1 minus 1/4 z inverse divided by, we began with 1 minus 1/3 z inverse into 1 minus half z inverse. Identify the poles. Identify the poles. Identify what are called the system poles now. Where are the system poles? Here they are at 1/3 and half. Now, of course, we are only going to deal with the solution of such equations when the input also has a rational, or the input is also a sum of what are called poly x terms. So, we shall assume the input is also a combination of what are called poly x terms. I will explain what a poly x term is. Poly x refers to polynomial multiplied by exponential. So, for example, you could take the poly x term example of a poly x term n squared plus 5n plus 1 multiplied by say 1/5 raised to the power of n. This is the poly x term. This is the exponential part of the term, and this is the polynomial. Polynomial in the natural domain variable. So, poly comes from here and x comes from here. A polynomial in the natural variable multiplied by an exponential is a poly x term. Now, of course, you can see that a pure exponential is also a poly x term with the polynomial of degree 0. A pure polynomial is also a poly x term with the exponential factor equal to 1. A constant is a very special case of a poly x term with the degree of the polynomial equal to 0 and the exponential factor equal to 1, and so on. So, all these are covered in the class of poly x terms. So, when you have a poly x input, as we call it, that means an input which comprises of a sum of poly x terms, we can solve this linear constant coefficient difference equation very easily. What we do is to identify what we call the input poles now. Now, here for example, the pole corresponding, so the pole corresponding to this poly x term is 1/5, but with a multiplicity of 3. That means 1/5 taken 3 times. Why is it taken 3 times? Because there are 3 coefficients in the polynomial. The polynomial is of degree 2, so it has 3 degrees of freedom. The constant part of the polynomial, the first degree part and the second degree part. So, as many as are the degrees of freedom in the polynomial, so many times is that pole repeated. If the polynomial is of degree 0, of course, that pole occurs with multiplicity 1. That means it occurs only once. If the polynomial is of degree 1, that pole occurs twice. If that polynomial is of degree 2, as we see here, that pole occurs 3 times, and so on and so forth. Now, of course, you must remember, even if you have just an n squared term and a 0 degree term, you must still assume that you have a repetition 3 times. The pole is repeated 3 times. It is the highest power of n that matters, right. So, essentially the multiplicity of the pole is 1 more than the highest degree of highest power of n in the polynomial. Is that correct? So, suppose you apply, now let us take the simple case. Suppose you applied this poly x term as the input xn, of course, valid only in that region 0 to 20. Now, a remark about how large or how small that region can be. Large is no problem, it can go all over the integer axis. Small is a problem. You cannot make it smaller than the degree of the difference equation. That means the highest pass sample that you need to deal with. In fact, here you need to deal with 2 pass samples. So, you cannot just assume that this difference equation holds for 3 samples and then solve it by the approach that we are using. If the length over which this difference equation holds is large enough to cover the span of the difference, span means how many samples you are involving at a time, then it is valid to use the procedure that we are describing. Otherwise, there is no solution but to operate the difference equation step by step. So, of course, you know yn in terms of yn minus 1, yn minus 2, let us go back to that difference equation. So, if you look at it, you can always sit down and solve it term by term, let us go back to this equation here. So, here you have yn is 5 by 6, yn minus 1 minus 1 by 6 and so on. So, if you know y of minus 1 and if you know y of minus 2 and you know x of 0 and you know x of minus 1, then of course I can find y of 1 or y of 0, I am sorry. Once you know y of 0, you can go one step further. you can find y of 1. So, you can keep solving this difference equation step by step and obtain the output, that you can do when the difference equation is valid only for too small an interval, but that is not a practical way of doing it when it is valid for a very long time. And what we are describing is a process for solving it when it is valid for a very long time. If it is valid for a very small time, it is not worth doing all that we are talking about, right. Anyway, so long enough means, long time means long enough for all the samples to be covered, samples that are involved. Now, in this case, we say the system poles are at 1/3 and half. The input poles, and with each pole you write its multiplicity. The input poles are at 1/5 and with a multiplicity of 3. Now, we write down what are called the union poles. We write down what are called the union poles. Now, what we mean by the union poles are the poles of the system union with the poles of the input. Now, how do you take, now I said union, not union means when you have a common pole, you must bring them together. Now, of course, in this case there is no common pole, right, but suppose we also had one more, we had a 1/3 with a multiplicity of 1 here, also in the input, we introduce that too. That means the input is a combination of two poly x terms, a 1/5 to the power of n multiplied by a polynomial of degree 2 plus a 1/3 to the power of n multiplied by a polynomial of degree 0. Suppose that the input is a combination of two poly x terms. What would be the union poles? Now, look for the common poles. Which are the common poles? 1/3. 1/3 is common. Now, 1/3 occurs with multiplicity 1 here and multiplicity 1 here. So, in the union it will occur with multiplicity 2. Half occurs with multiplicity 1. 1/5 occurs with multiplicity 3. This is the set of union poles. Is that clear? Now, once you have the union poles, you know the form of the output immediately. You know the form of the output immediately. What is the form of the output? The form of yn. Now, take each pole in turn. 1/3 occurring with a multiplicity of 2 contributes a 10 plus a 11 n times 1/3 to the power n. Half with a multiplicity of 1 contributes a 20 into half raised to the power of n. Is that correct? And 1/5 with a multiplicity of 3 contributes a 30 plus a 31 n plus a 32 n squared into 1/5 raised to the power of n. This is the form of y. Is that clear? Is that clear? Yes? Any questions on this so far? This is a very important point. If you understand this, half the job is done. Now, all these A's, A10, A11, A20, A30, A31, A3, all of them are unknown constants. We have to determine the constants. How do we determine the constants? We determine the constants by imposing the constraints that are given to us. Right. So, the constants are determined are determined from the system constraints right. Now, in fact, what do you mean by the system constraints? One constraint is the LCCD itself. So, put this yn back into the LCCD and some constants will emerge on their own. Then take into account the conditions on y that are given to you. Some more of these constants will be constrained. Is that right? So, I give you a little exercise to help you understand this concept better. The exercise is as follows. Obtain yn for n equal to 0 to 100, given that yn minus 5 by 6 yn minus 1, or we will do the same thing, 5 by yn is equal to 5 by 6 yn minus 1 minus 1 by 6 yn minus 2 plus xn minus 1 by 4 xn minus 1 and xn is equal to 1 by 5 raised to the power of n for n equal to minus 1 up to 100. Y of minus 1 is equal to 2 and y of minus 2 is equal to 4. Okay, so I leave this as an exercise for you to work out using the process that we have just described. All right. Now, one remark about resonance. One remark about resonance. We briefly alluded to resonance in the previous lecture. We said resonance occurs when there is a coincidence between system and input poles. So, for example, we could take xn equal to un. What is the Z transform? The Z transform is 1 by 1 minus Z inverse with mod Z greater than 1. Let us take Hn to be the same sequence. And whereupon you have Hz is also 1 by 1 minus Z inverse with mod Z greater than 1. Now, Yz of course would be 1 by 1 minus Z inverse the whole squared with mod Z greater than 1, and we know the form of Yz. The form of Yn would be of the form some A0 plus A1n times un. Now, it is very interesting. Here is a system where the input of course has a pole located co-located with the impulse response, it is the same place. If this were to be treated as an LSI system with this impulse response, that LSI system is unstable, because the input is the impulse response is not absolutely summable. So, it is an unstable system. But what we see is where this instability is manifested. The instability is manifested when we irritate the system by giving it the same input as the impulse response, otherwise that instability is not manifested in this system. Here you have irritated the system by giving the same input as the impulse response to it, otherwise the system is unstable, but it is an unstable system in a very hidden way. So, as I say, latent, it is not easy to identify the instability in the system. It is that proverbial case where you need to find a cause to irritate the system. That cause is giving the input which is the same as the impulse response. If you give it any other kind of input which is absolutely summable, for example, if you were to give it some other complex exponential sequence, not this constant, you would find that the output is bounded. If you give it a sine wave as an input starting from some point, you would find that the output is bounded. But it is for this troublesome case that the output becomes unbounded. Of course, this output is unbounded. Now, some people like to call such systems marginally stable. Of course, that marginally stable is only an informal term. Now, you understand why marginally, because it kind of is stable in most cases, but then it has these troublesome cases where it manifests its instability. Okay. Now, this idea of resonance is an idea which is used very frequently in analog circuits. Resonance happens when the input and the impulse response match, and the consequence of resonance is that although the input and impulse response by themselves might be bounded, the response is unbounded. In fact, this used to happen when soldiers marched across a bridge. This is a common example given. Typically, a bridge is constructed so that it remains stable with all its mechanical elements. But there are certain unfortunate frequencies of resonance in a bridge. When a bridge is constructed, the mechanical elements could have certain resonant frequencies. And when people randomly walk across the bridge, there is no problem. None of those frequencies are given in a significant way. But when you have these soldiers marching in strict rhythm across the bridge, if that rhythm happens to resonate with the system frequencies, bad luck, the bridge begins to oscillate, and the output or the bridge oscillations can grow without bound, and the bridge can collapse. This was observed many times when soldiers marched across a bridge. And people were puzzled, why should it happen? When people walk randomly, nothing happens, but when people march in rhythm, suddenly you have resonance. Yes, there is a question. The question is, if you have if the system allows the output to grow without bound, where is the question of conservation of energy? Now, if you look at it that way, an unstable system is only a concept. So his question is, where is the conservation of energy law valid? Well, actually, yes. I mean, therefore, an unstable system can only be approximated. For example, if you have a bank account, you will never put your money into a bank where the bank account is a stable system. You would like your money to grow without bound in principle. But of course, money cannot grow without bound. There is a finite limit to the economy of the country. So, an unstable system is a concept. It operates unstably up to a point. For example, when a transistor starts getting heated, and heated inordinately, that happens up to a point where the transistor remains a transistor. After some time, it burns. Then that system disappears. So, instability is a concept and valid only for a certain time. Anyway, with that observation of resonance, we conclude this lecture, and we shall in the next lecture go deeper into the question of when rational systems are stable and causal.